So it's done now.
I think we obviously many students not did not understand very clearly about transformation, and that let me spend about a few minutes to talk about transformation, so you can understand better. We know that and let us write the m and w double dot plus w dot plus the k w equal to b f u. All right. Now, if we assume that w equal to aq, then we'll be able to write down m that the so that means m we sub this w here. That means m free q double dot. This is a constant matrix, right? And this w is my physical coordinate. Okay, this q is my let me see, just call new coordinate. Right. Then if we sub this one into there, then I can write down that phi q dot plus k phi q equal to b f d. Right. And now I multiply this matrix by 3 transpose 3 q dot plus 3
Q double dot.
z
Q double dot.
2 double dot phi transpose 3 q dot plus 3 transpose q phi q equal to 3 transpose b f u. All right. Now after that, then we say, because I explained to you that there's such phi that we can that make me equal to a diagonal matrix. Make me equal diagonal matrix. Plus, then we have this matrix. I assume that we have alpha I plus beta omega square, right? That's what I assume, like that. And this is like matrix plus, this is the my omega 1 square, 0, 0, 0, omega 2 square, 0, 0. Wait a second. I forgot one more thing. I forgot many important things here. That this equal to that. This is my Q1 double dot, Q2 double dot, Qn double dot, plus let me write down really much more clearly here. plus alpha 1 0 0 0 1 1. Okay, let's write it down. I said this plus beta omega 1 square 0 0 0 0 omega 2 square 0 0 0 and that times Q1 Q2 dot dot Qn dot, right? Then plus omega 1 square 0 0 0 omega 2 square 0 0 0 omega n square times Q1 Q2 Qn plus here we have a matrix called 3BF. Then I have Q1. I have U1 here. U. I didn't expand that U yet. Okay. All right. That matrix makes them to be identity matrix. This I call identity matrix IN. This identity matrix. All right. And this is a diagonal matrix contain all my frequency in this matrix there. You have any questions? I hope you ask questions here rather than after the class, because your questions may be applied to all the students there. Any question about this? This alpha and this beta is a constant. This is not a matrix. This is a scalar. This is a scalar. All right? Any questions?
The question I want to ask is the phi, the constant matrix phi.
Yeah.
Well, based on what matrix do we use to derive it?
Okay.
Based on the mass
The
matrix.
same things. If we know all three matrices, in matter of fact, if we know M and K, if I assume this proportional that, we know M and K, we can derive the three matrices. There's a way to derive that. That's, you don't need to make a guess on that. In matter of fact, this three matrix is nothing but the eigenvectors matrix of the system. Not just on the M, not just on the K. The system eigenvector matrix. All right, I did not derive, I did not explain that yet, but I will show you by example. I think example is easier to understand than this theory. So let us go back to that 2 degree of freedoms, the 2 degree of freedoms matrix. All right. All right. Now look at this 2D freedom matrix. As a matter of fact, this one. This is the eigenvector matrix of K because M is 1, 0, 0, 1. So they're eigenvectors. Forget about that. All right. So that is the eigenvector matrix of K. That's all.
Normalized.
Normalized. Yes.
Then what if the mass matrix now is not an identity matrix?
Okay. Then that will be eigenvector matrix of M inverse K.
And inverse. That's a big difference.
Okay. There's many. Let me explain. We did this all mathematics now. That's become a. We gotta go back to talk about fundamental metrics still. That's that's mathematics, but that's true. Okay. Now there's another question. M inverse K is not symmetric matrix. All right. Although they are not, but they have a property of symmetric matrix property. Okay. Because the real system, assume we don't have damping, the real system, the eigenvectors must be real. I mean, for the second order system. Okay, let me just let me go further.
Though it's not symmetric matrix, but we will use it to derive
But
its eigenvectors.
Yeah, but when you solve it, it's still real.
Still real.
Yes. So this is what we call it's a you can call them it's a virtual symmetric matrix. they do possess the symmetric matrix properties, but it doesn't look like a symmetric matrix because this is real system. You have doesn't matter how mathematics you use, the result got to meet the real system's properties, right? That's true. Otherwise, the math is not good. the physical system is always good. Yeah, there cannot be no good, right? Let me explain to you. I think this is a good question. I didn't really try to explain it, you know, and but I'm glad you asked that question because that's really maybe tell you what we do. Matter of fact, you know, I honestly I really like linear algebra. I enjoy it because I can leave. For example, in real world, everybody live in a four-dimensional system, four-dimensional space. But GPS gives you the position for your point, and then plus time. That's it, right? But in a metric theory, you can live in an n-dimensional space. It's more than 4, 5, 6, 7, right? Like that, and it's fun, a lot of fun. All right, let me give you just. Let us look at just only n cases. This is I call the token in our class now. Okay. N w double dot plus kw. Let me give you some magics. All right. Assume let W equal to n half Q. Let's just make a look at that. Okay, Q. Half. I'm say half. The mathematics, can you get a half? Also negative half. The answer is yes. I show you later, but assume that you assume you accept these transformations. That's one kind of transformation. Now forget about Q, because that will confuse you for that. Say Z. Okay? Then if I do this, then M minus 1 over half Z plus Km 1 minus half Z equal to BFU. Right? Agree? All right. Then I multiply another half here, M minus 1 half plus M minus 1 over half Km minus 1 over half Z equal to, talking about Z double dot here. This is Z double dot. Okay. Z double dot here plus equal to BFU. All right. Then that equal to how much? That's equal to 1. Identity. Identity times Z double dot plus M1 K M minus half Z equal to M. I forgot one term. This is supposed to be M minus half BFU. And that's M minus half BFU. Agree? Right? This is a symmetric matrix. Okay? So M is a symmetric matrix. M, that is a symmetric matrix. M half is also a symmetric matrix. So how can I make a matrix half? Right? Matrix half. You know, a scalar M half is easy, right? Square root of that. The matrix half is it's easy to solve too if you really like to know how to do it. It's easy. All right. Then I call M equal to a, well, I don't know, the eigenvectors N, let us call the psi minus, then eigenvalue a lambda of then psi. This is equal to psi 1, psi 2, psi n, and lambda 1, lambda 2, lambda n, 0, 0, 0, 0, 0, 0. Okay, and that's inverse. Then multiplied by E1, E2, psi 2, to psi n. Okay. Then I crank, so M minus inverse half equal to the same eigenvector inverse, then that minus over half. And that half is nothing but everybody got have take a square root and inverse. The eigenvectors of this and eigenvector of that is the same. If you don't believe me like that, it's easy to do. You just multiply this by itself. And what do you got? I think there's a second. Let me go too fast. Let us look at this. Don't look at half here. No minus, 1 over half. How about that? Just 1 over half. It's easy enough. Then let us look at that. I'm solving this over half. How about that? Okay? I jumped too fast. I don't want to minus there. I just say I want to solve half, because minus half just inverse of that, right? Okay. Now m half times m half equal to psi dot half, psi dot, psi half, and that equal to right? This is equal to what, right? Right? Agree? That means the eigenvectors for the half is the same eigenvector for the m. Agree? All right. Then how can I solve half? Just make this inverse. Make this inverse easy. That inverse times that inverse times. This is matrix. That's a simple sense.
That's singular value decomposition.
Oh no, this is eigenvalue decomposition.
Yeah.
Yeah, this is eigenvalue decomposition. Because a mass matrix always positive definite. Matrix always positive definite. This is all positive. So when you square root that, no problem, because this is all positive. Now m positive definite, that means all eigenvalues are larger than 0. Okay? All right, well, we take this chance to refresh your memory about the matrix, right? It's not bad. Any questions? I like questions. Questions is always good. That means you are listening. That helps. That help me. That help yourself. Help other students too. Any questions? Any questions?
Well, the half of the matrix of the eigenvalue was bigger half.
This, okay. If I say half of this, I claim that half that means take only this half and multiply that. That's what I say. I claim. I say is this true or not? And this is proof it's true. Okay. If I say this is my formulations, and then I say this multiple itself, that becomes the phi. Do you think that's become n
So I just take the square root of the
of eigenvalue?
eigenvalue.
Right, eigenvector is don't do anything about eigenvectors. Like you can do anything about that. Because eigenvalue is diagonal, so it's easy just take all the eigenvalue you have. That's all. Okay, so I say this is my half, this is my formulation, and I prove to you it is right. Okay. Right, and this is the proof. Right? This is the proof. That's the proof. And this equal to m. That's the proof. Yeah. So if I accept this and say, okay, I prove it for you, that multiplied by itself equal to m. Yeah. So m half and m, I can back to other m. Understand? Okay? And that's very interesting. There's very interesting things going on here. So that, if you want to solve that, so you can solve this. If you say I'm not comfortable to compute eigenvectors of m inverse k. Somebody say, well, m inverse k is not symmetric, so it doesn't look like right. Then you can do it this way. You make it half first. Inverse times k has m half first, and then you saw eigenvector of this matrix. And the eigenvector of this matrix is very simple because what? Just think about it. If this is a scalar, this scalar, this scalar, what does that mean? It's k of n. Right? Do you think this is k of n? Right? What is k over n? Omega squared.
Yes.
If this is scalar, this scalar is k over n. It's nothing but k over n, right? That's it. So don't be scared by the matrix. It's nothing but just scalar. If you think about that matrix like a scalar, you are right. But just don't change the order. You say, I want to move this one to that one. Can't do that. Other than that, it's the same thing. Now, any more challenge now? You know, I'm glad you ask the questions, because you ask questions, I then understand what I can do for you. If you don't ask questions, I should understand. That's sometimes it's not a good assumption, but that's that's the way because I know this kind of things so many years. It's easy for me to just jump quickly. All right, I hope you understand about this, and this is very pretty, you know, and it's in the early days I really use this matrix too. And this is a nice matrix to do because it's symmetrics. So when you deal with symmetrics, you're more comfortable. Why? Because all eigenvectors are real, eigenvalue are real, and I can think about it better way. Okay. So can I go back my notes now? It's good enough. Okay, let's go back to the notes here. All right. So this is more general, and the notes is just 2 by 2. And this 2 by 2 matrix, you have to be look at carefully, because now the advantages of the transformation from this physical coordinate, from W, that's a physical coordinate, W, that's physical coordinate, to the Q, that's motor coordinate. The advantage is you decouple the ordinary differential equation to become uncoupled equations. So when you solve this, you have homework. And when you solve this, it looks more complicated. When you solve this, you can look at this, each molecule, Q1 and Q2, you can look at them as a 2 different single degree of freedom system. Independent. And they couple only through U tilt. U1 tilt. U1 tilt will have, U1 tilt will, if you look at this carefully, U1 tilt means minus 1 U1, minus 1 U1, minus U2. And then U2 tilt is minus 1 U1 times plus 1 U2. So the couple through the input, in here the couple through input, but their coordinates are not coupled. So when you look at their transient response, they are not coupled. Okay. When you look at their steady state response, then you got to go back to, you transform them back. So you look at each individual single degree of freedom system first. After that, then you can multiply that Q back by this phi to become your physical coordinate. Okay, then I look at this. Okay, now the FIF for each system. From U1 tilt to Q1, U1 tilt to Q1, only this. There's no nominator. You have only denominator. Don't you think that's much easier? Right? Agree? The same thing here. Plus, if you look at this carefully, this 1, that's your omega 1 square. The 3 is omega 2 square. So omega 1 is square root of 1. Omega 2 is square root of 3. So you can look at your natural frequencies from these equations. So when you plot, look at the next page. So this we call G1 tilt omega, G2 tilt omega. If you remember, you can go back to a few more slides. I talk about only 1 degree freedom system. It's just like that. Do you agree? Agree? Yeah. It's exactly the same as if you go back to look at that 1 degree freedoms. This 2 degree freedom. You go back to 1 degree freedoms. That's the message why we want to transform to the motor coordinate, because that's like this. That's 1 degree freedoms. Agree? That's 1 degree freedoms. That's 1 degree freedoms. Do you think this is almost the same thing as your Q? Q1 look like this form, Q2 look like this form, right? Agree? That exact the message I try to pass to you today. That message is, doesn't matter how many degree freedoms you transform to the motor coordinate, you can look at them to be only n single degree freedom system adding together by your input. Okay? Now the message is clear enough, you think? Okay, let's look at this. I think it's good. And you will be impressed by the next plot. Okay, because that's the plot. Look at the plot. That's the two plots. Two single degree freedom plots. This is the blue line is the this is the monocoordinate 1. The green line is monocoordinate 2. But don't forget that's a tilt. G1 tilt, G2 tilt. That the coordinate is different. That's from U tilt to Q. Okay. And if you look at each individual plot, it's much simpler, right? No, there's no zeros. There's no zeros. And where's zeros go? All right. And look at the phase plot. It's, I think it's much prettier like this. And it's easier to understand too, because that's nothing but just only a single degree freedom system. All right, where does zeta go? Okay, let us look at that. Where does zeta go? All right, but we need to transform them back. And this is my phi. Well, I happen to I use a different notation now, but it's just nothing but the phi you have there. And you need to do like that. This is diagonal, and then you have a phi times this diagonal to phi transpose, and that phi is this half plus by half 1, and then you want to add together, you add back. Your zeta come back. Your pause is the same point anyway. It doesn't matter it's in the motor coordinate or in the physical coordinate. The pause can be the same. Cannot be different. Because look at this. That's your denominator. Did you remember that? That's your denominator for your second order system, for your couple system. This is a denominator. So you plot, it basically you have a two plot from your denominator. When you add together by the transform matching matrix, then you get all the couple back. That means if you want to look at a physical coordinate, that's the plot you want to look at. You want to look at the motor coordinates, that's the last one is the one you look at. So depending on what kind of plots you want to see. In NASA, some people like to look at the motor coordinate plot. They think this plot is prettier. And so if you have many modes, you have a lot of this kind of plot. You can see a lot of this kind of plot. And it's very pretty. Think about it. If you have 10 plots like this, or like that, oh, you can have a lot of line. Okay? So when you look at the plots, you want to ask, I want to see the plots in physical coordinates or in motor coordinates. Now, any questions? Understand a little bit about motor coordinate now? All right? Looks good? Are you comfortable about it? Okay. Let us move further. Okay, so I put all plots together, and you can see the differences between the motor coordinates and the physical coordinates. And of course, so this is only very theoretical plots and very clean. In the real data, it won't be that this kind of clean. Not so easy like this. You won't see like this. But anyway, let's give you some idea. And I give you that transformations. That transformation is easy. So if you want to understand the transformation, monoclonal transformations, you just look at these examples. You understand this example completely, then you will be able to understand more than 2 degree of freedom system. It's nothing but just add more monoclonals. That's all you have. And for n degree of freedoms, you in the left hand side, and except in additional to blue line, green line, you have another purple line or other some black line, whatever, like that. That's all. It's very simple. Okay. All right. At the end, on the follow-up slides, I won't talk too much about this because this proof, I'm proving to you the discrete spring system can be used to derive continuous system. All right. So I'm not going to talk in very detail about that because that's you can try to read it. From matrix, a lot of matrix, when this the order going to infinite, then what happens? And when it large MDOF, then I start doing the become delta W, delta X, very small distance. And after that, then you can in the limit. The key is I want to show you that. Is become a partial differential equations like this. The last is becoming partial differential equations, equation of motion in the limit, and then in the next part, this one is a PDE. So any continuous time system you can really express by a finite discrete system. That's what I'm saying here. But if you look at that, somebody argued in the early 80s, some engineers, some professors don't believe PDE. Why? They say the whole world, doesn't matter what system you have, they're supposed to be discrete. You agree? No? So you believe it's the continuous or discrete?
I think they are supposed to be discrete.
You think they are discrete?
Yeah.
Why?
Yeah, because everything happens in space and time.
Well, I think the argument is because any system is composed by what? By molecular, by atom, and they are discrete. Right? So there's a finite number of atoms, although there's a very large numbers, but there's a finite number of atoms to create a system. Well, that is a little bit too much, but I'm saying that. But anyway, that's in the 80s. The NASA researchers, they are divided. Some people, some of my friends believe, we have to use the PDE model. That's because that's more accurate. And another set of people say, no. There's not such continuous system. There's not such sense. Anyway, that's just a cool argument. Anyway, I enjoy that. All right. Okay, so this is we call distributed parameter system. In early days, that part of I already told you, part of my friends, and also friends, they prefer to use this kind of PDE to design control, and other people like to use this MK to design control. So, so they do have a completely different approach to design control. And that's, but I myself, I'm not really involved in PDE control, since because that's a mathematician job. It's not engineer. It's an engineer's job. That's what I told him. All right. This is some other continual distributed parameter system. And anyway, I jump around it quickly, and you're welcome to read further, but I won't give you any test problem for this, so you don't worry about it. And natural frequencies for distributed parameter system, the frequencies infinite. There's infinite frequencies. All right, and there's a natural mode, and I wanna show you. I want to show you some of the things, which is like this. This is something my favorite. This is the mode shapes. All right. The mode shapes. If you look at this one, the first one is the first bending mode. So the mode shape will look like this. They vibrate like this. And the first torsion mode, they vibrate like this. And first the vertical mode, they vibrate like this. And in the real vibrations, they mean they are a combination of all these kind of motions. Of course, each motion will be weighted by some constant, so that that become a real vibrations. But if you happen to excite your system using the frequencies of these mode shapes, then of course you will excite these mode shapes come out. But your external forces, the frequencies for external forces has to be the same frequencies as these mode shapes. Then you can excite this mode shape come out. NASA engineers, they really prefer to look at the 3D animations of these kind of motions, so they can feel the structures is really stable, or the structure maybe in danger if you have this kind of mode shape come out, and so on, something like that. So anyway, I just show you all kind of different mode shapes, and this is the mode shape we are talking about. Mode shapes. The phi, the transformation phi, that's the mode shape we are talking about. That's the mode shapes. So they do have a physical meaning, all the mode shapes. They do. If you oscillate with the same frequencies, then your vibration motion just like this. Okay, well, let us take 10 minutes off, and then we finish these chapters. And I'm going to waste of time and have another about 50 minutes. Then I want to talk about the TMD. All right, there's a chapter called TMD. That chapter TMD.